Hello, we are Team Rite Solutions, and our project is on-premises large language models. Our goal was to support the internal document drafting process at Rite Solutions by harnessing the power of generative AI and LLMs specifically in our case. Our team would like to acknowledge our ELECOMP Capstone technical directors, Jacob Wojciechowski, Alexander Moulton, and Thomas Santos. Their support and guidance throughout this past year have been key to our project's success. We would also like to acknowledge our consulting technical director, Jamie Gagnon, for his constant and insightful support on the project at weekly Capstone meetings. Our team consists of 2 computer engineers, myself, Demetrius Petru, and Sopran Lauren. Our sponsor company, Rite Solutions, is always on the lookout to incorporate the most cutting-edge technologies into their products and workflows. With the relatively recent boom in generative AI, and especially LLMs, their motivation to sponsor our project was to take a step toward figuring out how to effectively incorporate these models in the everyday work of Rite Solutions employees. To work with LLMs, users typically need to connect to some external service or API and send over data to perform fine-tuning or some other context-based task. Throughout the project, our focus has been on developing a system that can be hosted locally to keep in line with Rite Solutions' commitment to producing secure products that keep customer data from potentially being leaked. To understand our project well, it is important to have a high-level understanding of how LLMs work. These models consist of complex networks of weights or probabilities that together decide what word to generate in a sequence. When the LLM is trained, it is fed a large collection of documents that help it decide how to adjust its weights. In this way, it learns the relationships between words and how natural language is constructed in general based on the text it sees. Once an LLM is trained and ready for use, we perform what is called inference, or prompting, to receive a generated output. A user's prompt is fed to the network, and it then decides what the next most probable word is within its vocabulary. This process is repeated, feeding the original prompt and each word generated by the model until an end-of-sequence token is generated and the model is done. Of course, an LLM's vocabulary is much larger than just the 4 words shown here for illustration. There were a few key things we needed to keep in mind throughout the project. First, the goal of our fine-tuning was to teach the LLM to output long, document-like responses for the purposes of drafting. Second, the fine-tuned LLM needed to be informed on the topic at hand based on the data we used for fine-tuning. Third, the system needed to be hosted locally so that we could keep in line with our 4th point of focus, security. To avoid leaking proprietary or sensitive data, the system needed to be able to run detached of any external services.
The ultimate economic impact is felt through the increase in productivity by saving time during the drafting process. When making draft proposals normally required by the government, a team of engineers and analysts at Rite Solutions have to sit down and spend weeks at a time to come up with a draft. With a large language model, we can offload all that work onto the model and do that in minutes. The model can produce various different proposal documents depending on the situation quickly, effectively saving Rite Solutions time and allowing their end users to work on other tasks. The anticipated best outcome, which was achieved by our team, was to produce an inference system in the form of a large language model and the documentation for it. In terms of design, the model must produce inferences that are fast for the amount outputted. It also has to be fine-tuned so the outputs are document length and taking into account the context of the documentation fed into it. Lastly, it has to be user-friendly, easily producing inferences for users who may not be familiar with the system. As for the documentation, our end goal was to make our produced model easy to replicate. To do this, we provided an installation and usage guide, a prompt engineering guide to describe how to create an ideal prompt for optimal inferences, and an overall evaluation report to describe the research, results, and all decisions made. The summary of team key accomplishments includes research on the background of LLM sizing and the hardware requirements, the fine-tuning pipeline including the ARC subscraper, dataset generator, and fine-tuner, an inference module, and complete documentation in the form of evaluation and user guides.
My first main focus on the project was researching how to host and work with LLMs locally, how to source and collect fine-tuning data, and what our options for fine-tuning approaches were. I also looked into hardware needs, mainly GPU related, for working with LLMs and performed tests to measure GPU usage on a few LLM tasks. My largest contribution was implementing the fine-tuning pipeline, which I will go into next. Finally, I performed our fine-tuning evaluation to gather conclusions regarding its effect on model output and how to interpret our overall work. The fine-tuning pipeline consists of 3 modules. Arxiv Scraper gathers documents based on user queries from the Arxiv database to form fine-tuning datasets. Arxiv is an open-source database that allows researchers to easily upload research papers and other technical documents, and for that reason, it contains a host of information on the most cutting-edge topics, especially computer science and AI related. To perform fine-tuning, we use tools from the Hugging Face Transformers library, and it requires datasets to be in a special format for its use. DatasetGen takes the datasets made from Arxiv Scraper and converts them to the Hugging Face dataset format. Finally, FineTuner uses the created dataset to fine-tune the LLM of choice, the Mistral 7 billion model in our case, which was released in September 2023. Next, we'll look at these modules a bit more closely. Arxiv Scraper starts out by receiving a query from the user that it uses to form a request to the official Arxiv API. The API returns an XML document with links to the documents in its database that are relevant to the query. These links are then used to retrieve and save locally the actual PDFs from the Arxiv database. Finally, the relevant content from these PDFs is extracted and appended to an entry in a CSV file. At the end of a scraping session, Arxiv Scraper has formed an entire dataset based on a user query. The next step is for the CSV dataset to be converted into a Hugging Face dataset for use in fine-tuning. The converted dataset is then fed to the tokenizer of the FineTuner module, where each document's text content is chunked into tokens that the LLM can understand and work with. Along with some important training configurations, the tokenized data is provided to FineTuner's trainer, which performs the actual fine-tuning. It is important to note here our approach to fine-tuning. Parameter efficient fine-tuning, or PEFT for short, is a technique that creates a new and small subset of parameters called adapters that are trained rather than adjusting all the weights of the LLM or full fine-tuning. This approach makes it possible to fine-tune these large models. After the adapter weights are trained, they need to be merged with the original LLM that has remained untouched. Then the model is ready for use as a fine-tuned LLM. The following are some of the most important conclusions that we gathered during our fine-tuning evaluation. First, it is fairly easy to encourage LLMs to output long and document-like pieces of text if the training data is lengthy as well. Also, a fine-tuned model will naturally produce coherent text that matches the overall length of the training data. Second, the PEFT approach explained in the last slide greatly alters the behavior and output style of the LLM despite the small amount of parameters that are trained and added. This does come at the cost of higher inference times, however. Third, fine-tuning a model that has already been fine-tuned to follow instructions well produces better results and does not affect the model's ability to produce long output. We used Mistral 7 billion as our base model in testing and the instruction-tuned version of this same model called Westlake for comparison. Finally, given how difficult it is to effectively evaluate large outputs and to form high-quality datasets with long text, it may be better to focus on generating smaller chunks of technical documents in the future. This way, fine-tuning datasets can be formed with shorter and more targeted prompts and responses, and performance can be evaluated more easily.
For my technical contributions, I worked on the benchmarking methods to gauge the quality of different LLM options. I also worked on the P-matrix assessments, and, using our P-matrix, produced a list of the top models to move forward with for our final fine-tunes. Most of my time was spent learning the inference module and working with different prompt engineering techniques. In order to provide a user-friendly solution to LLM inference, we utilized Text Generation Web UI. It allows us to interact with our models via a chat-like interface. The key reasons for using Text Generation Web UI are for the following reasons. First of all, it is completely local. It works by opening up a local server that can only be accessed by the user's computer. Secondly, the interface is accessed via a web browser, making the system very lightweight and requiring little overhead. Lastly, it is customizable and allows for easy modification of the hyperparameters that control our model's behavior. We employ various prompt engineering techniques in order to improve the effectiveness of our models. The first of these techniques is prompt manipulation, in which we change how we structure the wording of our prompts. By making our instructions clear and concise, we are able to better convey the qualities of an ideal output to the AI. As such, we are able to state any desired qualities, such as formatting and output length, as well as include or exclude any particular information. The second of these techniques is through the modification of the system message. The system message is an instruction to the model that acts as the overarching definition of the AI's purpose. By making changes to this aspect of a model, we can effectively change how the model interprets any requests that come into it. Lastly, we take advantage of retrieval augmented generation, which is a technique that allows for external data to be provided to the LM post-training. This information is then understood as context by the model and can be efficiently recalled during inference. In particular, our application of retrieval augmented generation, or RAG, takes advantage of the SuperBooga v2 extension provided in Text Generation WebUI. We use this extension by first inputting text containing the information we'd like the model to remember. The model then extracts any useful information from the text and converts them into embeddings. We utilize RAG as a technique for 3 reasons. Firstly, it does not use up any context length. Context length is a finite number that defines a limit of how many tokens can be included in the prompt and output. RAG avoids using up any of this context length, which allows us to include more information when we prompt the model. Secondly, it improves inference quality by providing the model with context that may be relevant to our main tasks. During inference, the model can call upon this context to generate educated responses specific to the task. Lastly, this technique is easy to implement and can always be updated to include new data, so the model does not need to be trained on a specific domain to be knowledgeable on it. A key aspect of the project is documentation, as it allows us to lay the groundwork for future work. The first of these documents is the usage documentation. It details the installation and setup of our pipeline and inference modules. It also explains how to use the pipeline. Lastly, it covers how to perform inference. The second documentation is the prompt engineering guide, which explains the techniques in detail and how to effectively use them. Images of inference before and after the techniques are provided in the guide to better convey their usefulness. The last document is our evaluation results, which goes over the data from fine-tuning, the key takeaways, and future directions for the project. To conclude, we have achieved the anticipated best outcome and have successfully completed the fine-tuning and inference pipeline. We are able to scrape the contents of technical papers through the ArcSIP scraper, convert it into a dataset, fine-tune a model with that dataset, and finally, perform inference. Additionally, we've learned ways to improve our outputs through prompt engineering and documented everything in detailed guides that show how to replicate our work. And lastly, the team would like to acknowledge Jacob Wojciechowski, Thomas Santos, Alexander Milton, and Jamie Gagnon for their continued support and assistance. And a special thank you to Dr. Harish Sunak for providing us with the ELECOMP capstone. Thank you.